Good morning friends. Today we will be going to discuss about some numerical problems of wire drawing. With the understanding of the numerical problem, we can really comprehend the entire process, and this is Somnath Chattopadhyaya from Department of Mechanical Engineering of IIT ISM Dhanbad, and this problem I have taken from a very renowned textbook MP Groover in the chapter of metal forming. So, as from the title slide we can see that the case is a typical case of wire drawing, where a starting stock with the diameter d suffix capital D suffix 0 and with this entrant angle that is alpha, that is a determining angle in case of wire drawing. It is entered into that, and there is a very specific length of critical length which is done in the draw die, and that is important, and the dimension is converted from d suffix 0 to df final, and f is the pulling force, and final work size is associated with the d suffix f final diameter. So, this is a typical case of wire drawing, typical structure of wire drawing. And let us see what is the problem associated with that. So, the problem is wire is drawn through a draw die, because draw die is responsible for taking that, and with an entrance angle alpha. From the picture itself it will be totally clear, the entrance angle is 15 degree, and starting diameter, which is initial diameter capital D suffix 0, is 2.5 millimeter, and the final diameter is 2 millimeter. That means 2.5 millimeter dia wire will be converted through these die to final diameter of 2.0 millimeter. And the coefficient of friction, that is important because that will determine the flowability of those material. And the coefficient of friction at the work die interface is 0.07. The coefficient of friction is 0.07, and that is a determining factor in terms of the process. And the metal strength, definitely strength is very important, because the ductility of all those things to be associated with which is ductile, then and then only we can draw a wire. So, drawability depends upon the strength coefficient, and the strength coefficient is designated by the alphabet K, and that is near about 205 megapascal, and a strain hardening exponent, because strain hardening exponent is also there in order to measure the flow stresses, and that exponent is also given from the problem. It is 0.2, and what we have to do, we have to determine the draw stress and the draw force in the operation. So, that is critical. In order to design this process, we have to know what is the draw stress required and what is the draw force in this operation required in order to appropriately carry out these operations. So, this is a typical representative problem related to wire drawing operation. So, this is again the picture whatever we have discussed about that drawing of a bar or a rod or wire, where initial stock is having the diameter d suffix 0, and that is entering into that to get the dimension of d suffix f, that is the final dimension, and the final work size will be there, and force of pulling force is there, and draw die is there, and some critical length associated with those length where it is attached in the inclinations against the die is given, and that is L suffix C. Now, we will go into the solution of the problem. So, area reduction in the drawing. So, in this drawing operation, area is reduced, area of the cross section is reduced. So, A0 is the initial cross section, A final is the final cross section, and that ratio is determined A0 minus AF divided by A0, that is the reduction ratio. So, in a drawing operation, the change in size of the work is usually given by the area reduction, that is typical associated with the wire drawing operation. So, area the reduction is given by the change in the area in comparison to the original area. So, R is the area reduction in the drawing, and that is nothing but a ratio, and it is divided by A0 minus AF in the numerator, and the denominator is the original. So, it is expressed in terms of, say, percentage. So, R is a ratio. And the draft is simply the difference between the original and the final stock diameter, because our drawing is for reduction of the diameter, and this draft is simply representation of the reduction in the diameter. So, initial diameter, that is d suffix 0, capital D suffix 0, original diameter, and the final diameter is d suffix f. So, the difference, definitely the original diameter will be greater than the final one, and the draft will be in millimeter and represented by the straightforward equation d is equal to capital D suffix 0 minus capital D suffix f, original minus final, and that difference in millimeter represented by the alphabet, small alphabet, that is d. So, that is represented as draft. And the true strain, it is coming from the formula from the handbook, and the formula is epsilon. Epsilon is the logarithm of A0 divided by AF. A0 is the initial area, AF is the final area. So, logarithm of A0 by AF, or logarithm of 1 by 1 minus r, 1 by 1 minus r, r is the reduction ratio. So, if no friction or redundant work occurred in the drawing, true strain could be determined as stated, because we don't assume that there is no friction or redundant work, and A0 and AF are the original and the final cross section, as we know that, and R is the drawing reduction. So, on the basis of that, we can find it out, the true strain in the drawing. Very easy to calculate with a very basic equation associated with that. And once it is there, then the flow stress, definitely we can find it out. The ideal deformation is given by the stress is sigma, represented by sigma is equal to y suffix f bar into epsilon, and y f into epsilon. And what is epsilon? Epsilon is the strain, and that is ln of A0 by AF. So, that comes out to be in that equation, very easy to understand. And once it is done, then we can go for the next one, and that is the average flow stress. That we have to know what is the average flow stress based on the value of the strain. And this is average flow stress, that is why it is given bar, and y is suffix f, and bar is there to represent that it is average. And average is equal to k into epsilon to the power n, that exponent divided by 1 plus n. That is also very straightforward formula related to flow stress associated with the strain and the strain exponent. So, y suffix f bar, that is average flow stress, is equal to k into epsilon to the power n, that is the exponent divided by 1 plus n. So, this is the value of average flow stress. And whenever we can put all those things there itself, in addition, the ratio is also another ratio is related with, that is A0 by AF, original area divided by the final area. And other variables that influence the draw stress are die angle. One more thing, that is called die angle, and that is the coefficient of friction at the work die interfaces. So, we have to determine the coefficient of friction, which is have a very important role to play, and the formula is associated with this coefficient of friction, that is sigma suffix d. Sigma suffix d is a function of average flow stress, and along with this friction mu, and then the alpha, the angle, die angle, along with those another component, that is phi, along with those is logarithmic expression. So, sigma d is equal to average flow stress, that is the y suffix f bar into 1 plus mu, that is the friction coefficient, divided by tan alpha. This alpha is entrant angle, die angle, along with phi into logarithm of A0 by AF. A0 is the initial cross section, AF is the final cross section, and draw stress is determined by, so this is nothing but a draw stress, and draw stress is defined in megapascal, and this is there, and according to that we have to calculate those value. And the draw force will be final area into draw stress, and that is easy, A suffix F into sigma d. Sigma d is the draw stress, and sigma d, whatever the formula we have come out of it, AF into YF into 1 plus mu by tan alpha into phi into ln A0 logarithm of A0 by AF, and that way we determine, that is the theoretical part of draw force, that is in terms of Newton. The power required in a drawing operation is the draw force multiplied by the exit velocity of the work. Quite naturally it comes out to be the power is equal to the force into the exit velocity. Now the phi is a factor, we need phi. In that equation we found out a phi, that is nothing but a factor, and this factor accounts for an homogeneous deformation. Some factor has to be, it is accounts for the homogeneous deformation which is determined for a round cross section. This is a typical factor, and we have to consider that, and that will determine on the d and this length of contact in the die. So it is a factor, we have to calculate that factor. We have some fixed value 0.88 plus 0.12 into d diameter divided by LC, that is the length of the die which is in contact with those workpiece while drawing these activities. So phi is determined in that, and we can definitely find it out that d, because in the previous cases that d is there, d is the average diameter. What is the average diameter? Original diameter, final diameter divided by 2. So that is d, and these LC, this is geometrically we can easily come out of that deduction, that L suffix c, which is associated with this inclination part associated with those drawing of those workpiece, and that is determined by d0, that is original diameter, minus df final diameter divided by 2 into sine alpha, that is the angle. So that is the value of L suffix c. And then phi, definitely, because 2.5 plus 2 divided by 2, that is 2.25, so average diameter is 2.25, and LC that has been calculated as 0.966 millimeter, 0.966 millimeter. So phi, that factor is determined 0.88 plus 0.12, that is already given, into the average diameter divided by LC, and that is 2.25 by 0.966, and that comes out to be 1.16. That phi factor is coming 1.16, coming of the deductive of all those values. So the area before and after drawing is very easy, because A0 is depending on those their diameter 2.5 and those things, and according to that so we can determine the value of A0, and we can easily determine the value of AF from the diameter itself, and the resulting strain also we can find it out the value, that is logarithm of 4.91 divided by 3.14, that comes out to be 0.446. And putting all those formula related to these average flow stress, that comes out to be associated with putting all those equations there itself, from there itself we can find it out. We can find it out those values, that is sigma d is equal to YF into 1 plus mu by tan alpha into phi into logarithm of A0 AF. So we are putting all those things in those values, and according to that we find it out that the stress is can be calculated. So YF and other things we can easily calculate it from there itself. YF is equal to k into e to the power n divided by 1 plus n. So we know that n is equal to 0.2, it is already given from the k exponent. exponent is 205 and divided by k 205 into strain to the power 0.2 divided by 1 plus 0.2. So that will determine the value of this thing. So whatever we have found it out, that the value of the strain is 0.446, that is E is of logarithmic of 4.91, for a logarithm of 4.91 divided by 3.14, that comes out to be 0.446. So 446 is there and 205 is the k, and exponent is 0.20 divided by 1 plus 0.20, that comes out to be 1.20. So this is calculated, and on the basis of that we found it out. Average flow stress is 145.4 megapascal, 145.4 megapascal, that is determined as the average flow stress. And whenever average flow stress is there, then we can determine the value of sigma d. Sigma d is equal to yf into 1 plus that mathematical expression mu by tan alpha, alpha is 15 degree, 1 plus into those values, and we put those values, one is 1.16 and is 0.446. So if you can find it out, that equation related to sigma d, we can easily find it out that sigma d is yf, we know that already determined, 1 plus mu by tan alpha, mu value we know that alpha 15 degree, and this phi value also we have calculated, and logarithm of a0 by af, that is also calculated. If we put all those values, then immediately we can find it out that sigma d, and that comes out to be near about for 94.1 megapascal. If we put all those values in those equations, we can come out with those values, that is 94.1 megapascal. And from that thing we can easily determine, the draw force. Draw force is a stress multiplied by the cross section area, final area of the cross section, that is 3.14, and the stress is 94.1 megapascal. So 94.1 into 3.14, that is multiplied in order to determine the draw force, and that comes out to be 295.n or Newton, 295.5 Newton, and that is the equations, and we can find it out, those draw stresses and draw force. Let me find it out. What are the things has to be determined in the question. The question was that we have to find it out, the draw stress and the draw force. So ultimately we can find it out. The draw stress is associated with 94.1 megapascal, and draw force is into this final area, that is 3.14, and that way we have arrived at this final value. So thank you very much for going through those numerical problem and solutions related to wire drawing. It is important for discussions and understanding of the typical wire drawing problem. Thank you.